Welcome to another episode of My Weird Prompts, an AI-generated podcast featuring the random prompts of Daniel Rosehill as answered by a revolving cast of friendly AI characters. Join us for deep dives into AI, technology, and whatever other random thing Daniel finds fascinating today. Subscribe on Spotify or your favorite podcatcher. Now, today's episode.
This episode was generated using artificial intelligence. Please verify facts.
Hey Herman and Corin. So I mentioned that, much to my chagrin, I spent some more time today peering into a computer box, and I finally got the riseable table thingy up and running, and that is at least saving my knees. But it still means peering into this small box with a screwdriver and going slightly crazy for a few hours until I say, okay, it's done. Turn it on, and then you hold your breath and hope that it works. But we did an episode about precision tools for those who are also building or tinkering with computers. And I mentioned that besides being a really great skill, in my opinion, it's a very thrifty skill to have. If you can repair your own computer or do your own upgrades, you can keep your older hardware still going. You can salvage parts and do a whole lot, and it's empowering and it's kind of fun, although it's sometimes crazy making. The reason that I think computer servers are particularly crazy making working on desktops is that everything is so finicky. It's all about these little screws and tiny connectors and millimetric precision. And when you open up the computer, now mine was built here in Israel, which I've mentioned the service on many podcasts. It's kind of a somewhat unique thing in which you order a computer, pick out your parts, they assemble it for free. So it's actually, I think, a pretty good deal. We have expensive tech components, but that is a pretty big service when someone will actually do all this. And by the way, this is what I've done before. I like tinkering with computers, but I don't particularly feel the need to put my own one together if there's some way to have someone else do it, because it's just a lot of work. But my question, Herman and Corin, is looking at the absolute insane precision through which these things come. And when you start opening up the case, you see, all these very carefully attached screws that are just precisely holding something in place, and only that screw will do, nothing else. And there's like a millimeter of clearance between some of the components and the others. So everything is fit together like this minuscule jigsaw that has to be perfectly assembled. My question is this, twofold really. Number one, if there's a computer service in Israel that does this for free, does someone have to do this manually? Because it seems like it just couldn't be worth their while. By which I mean, how can you do this process of hardware assembly? Can humans even do it in a way that's remotely cost effective? Is there this whole caliber of tools out there that are kind of semi-automated and literally seat, RAM, and all the rest of it that you need to do in a computer if you're starting from components? But the bigger question I have for the much more significant purchasing channel for desktops, which is that it's an OEM manufacturer. You buy it from the company, everything comes pre-assembled. I assume that that's fully automated. But my question again is, what kind of robots are able to operate at that level of precision? If we think of an average computer, you've got a case. Motherboard has to be screwed into that case very precisely in a way that doesn't introduce static electricity such that the thing would fry. Then you have to seat the CPU. You have to put on that thermal paste, attach the CPU cooler, which is, I think, the repair that I've done 3 or 4 times over the past 2 weeks. The CPU cooler seems to be the most finicky of all the things you can do with a computer. So maybe not a great place to rejuvenate my interest in this. But that's where it's very precise. You've got to get a backplate on, RAM in, CPU cooler line screwed in, all the wires attached to the motherboard in exactly the right pins, which are themselves absolutely tiny and hard to reach. So again, my question is just, how is this robotically done? If it is, and I guess we could ask the same question about laptops or any other type of technology that's actually quite dense with internal components that have to be put together in an insanely precise and detailed way, while also making sure that static electricity doesn't destroy the computer in the process. So it seems like a very challenging task for robotics, but I'd love to know, Herman and Corn, about how it's actually done. Herman and Corn, this one again is for you on My Weird Prompts.
Hey everyone, and welcome to another episode of My Weird Prompts. I am Corn, and I am joined as always by my brother, who I am reasonably certain spent his formative years trying to overclock a toaster.
Herman Poppleberry here. And for the record, Corn, that toaster had incredible thermal throughput once I swapped out the heating elements for nichrome wire from a hairdryer. It did not make great toast. It tended to carbonize the bread instantly, but it could reach peak operating temperature in under 4 seconds. It was a proof of concept for rapid breakfast delivery.
And that is exactly why you are the perfect person for today's discussion. We are diving into a prompt from Daniel about the absolute madness that is computer hardware assembly. He has been spending some time lately peering into the guts of a computer, dealing with those tiny, infuriating screws and the millimetric precision required to get everything running. He is basically asking how the industry survives when the physical reality of building a PC feels like performing microsurgery on a caffeinated hummingbird.
It is a harrowing experience for the uninitiated, is it not? You spend hundreds or thousands of dollars on these delicate silicon wafers, and then you have to use a tiny screwdriver and a prayer to put them all together. One slip of the hand, one static spark from your favorite wool sweater, and you have a very expensive paperweight. It is the ultimate high-stakes puzzle.
Exactly. And Daniel's prompt really hits on the tension between that delicate, manual process and the massive scale of the global computer industry. He is asking two big questions. First, how on earth is manual hardware assembly cost-effective, especially when some shops do it for free? And second, how much of this is actually automated at the big manufacturers? Like, what kind of robots are capable of seating a central processing unit, or plugging in those tiny fragile wires without frying everything with static electricity?
Those are fantastic questions because they get at the heart of how our modern world is actually built. There is this massive gap between the high-tech, digital image of a computer and the very physical, almost artisanal reality of putting one together. We think of computers as being born in a clean room from pure light, but the final assembly is often surprisingly tactile.
Let's start with that first bit, the manual assembly. Daniel mentioned a service in Israel where they assemble your custom PC for free if you buy the parts. From a business perspective, that sounds like a nightmare. You are paying a skilled technician to spend an hour or two fiddling with tiny screws for zero return on labor. How does that math work in 2026?
Well, the first thing to realize is that for a professional, it is not an hour or two. If you or I sit down to build a PC, we are double-checking the manual, we are cable managing for aesthetics, we are probably dropping at least one screw into the dark abyss of the power supply shroud, and we are definitely spending 20 minutes wondering why the front panel connectors are so small. A professional technician who builds 10 to 15 systems a day has a muscle memory that is almost frightening.
So what is their actual turnaround time?
For a standard mid-tower desktop, a pro can have the motherboard prepped, the central processing unit seated, the memory clicked in, and the whole thing mounted in the case in about 15 to 20 minutes. They do not read the manual because they have seen every variation of the LGA 1700 or AM5 socket 1,000 times. The operating system installation and stress testing happen in the background on a network boot while they move on to the next one. So, the labor cost is actually much lower than a hobbyist might think. We are talking maybe $15 of labor time for a $100 margin on the parts.
Okay, but even 20 minutes of a technician's time is not zero. Why give it away?
It is a classic loss leader, but with a twist of risk management. By offering free assembly, they ensure you buy every single component from them rather than hunting for the lowest price on individual parts across 5 different websites. They make their margin on the hardware markup, but more importantly, it drastically reduces their return rate. If a customer builds it themselves and bends a pin on the motherboard socket, which is incredibly easy to do, that is a customer service nightmare. The customer blames the board, the shop blames the customer, and everyone is unhappy. If the shop builds it, they know it works before it leaves the door. They are essentially buying insurance against user error.
That makes sense. It is basically an insurance policy for the retailer. But Daniel also asked if there are semi-automated tools for this kind of manual work. I am picturing something like a specialized jig for seating random access memory, or a machine that applies exactly the right amount of thermal paste. Do those exist in these smaller shops?
In small to medium shops, you do not see much in the way of robotics, but you do see highly specialized manual tools. The most important one is the precision electric screwdriver with adjustable torque settings. That is actually a huge deal. You do not want a human just feeling how tight a screw is when it is holding down a heatsink or a delicate M.2 drive. You want it tightened to exactly 0.6 Newton meters. These drivers have a clutch that disengages the moment the target torque is hit. It prevents stripped threads and, more importantly, prevents the board from flexing and cracking a trace.
Right, because if it is too loose, the heat does not transfer, and if it is too tight, you crack the substrate of the chip. It is a very fine line.
Precisely. And for things like CD memory or expansion cards, it is still mostly human fingers because humans have incredible haptic feedback. We can feel if something is misaligned in a way that a basic machine cannot. However, when you step up to the level of a large-scale system integrator companies like Puget Systems, or even the custom wings of larger retailers, then you start to see the semi-automation.
Like what?
You might see specialized pneumatic presses for things like the memory modules. Instead of a person pushing down on each stick and waiting for the click, which can actually be quite hard on the thumbs after 100 units, the motherboard sits on a custom milled tray, and a pneumatic press comes down with perfectly distributed pressure to seat all 4 sticks at once. It ensures that the pressure is even across the entire contact surface, which prevents the motherboard from flexing. They also use laser-guided templates for thermal paste application to ensure the piece-size drop is exactly centered every single time.
That sounds much more reliable. But let's move to the big leagues. Daniel's second question was about the original equipment manufacturers, the big names like Dell, HP, or Lenovo. When they are churning out millions of laptops and desktops, is that fully automated?
This is where it gets really interesting, and the answer is it depends on which part of the computer you are talking about. If you look at the motherboard itself, the green or black circuit board with all the tiny components, that process is almost entirely automated. It is a marvel of engineering called the Surface Mount Technology Line, or SMT.
I have seen videos of those. They are incredibly fast. It looks like a blur.
Oh, they are mesmerizing. It starts with a blank board. A machine applies solder paste through a laser-cut stainless steel stencil almost like screen printing a t-shirt. Then it goes into the pick-and-place machines. These are the robots Daniel was asking about. They have these tiny vacuum heads that grab components, some of which are the size of a grain of sand, like 0201 resistors, and fire them onto the board at speeds the human eye can barely follow. We are talking about 60,000 to 100,000 components per hour.
But those are just the tiny bits, the resistors and capacitors. What about the big stuff? The central processing unit? The cooling fans? The actual assembly into the case?
That is where the fully automated dream often hits a wall. For a long time, the actual assembly of the final product, putting the board in the case, connecting the wires, screwing in the drives, was almost entirely human labor. Humans are just much better at dealing with flexible objects like wires and cables.
That is the spaghetti problem, right? Robots are great at rigid objects, but a loose power cable is a nightmare for a traditional robotic arm.
Exactly. If a cable is dangling a few millimeters to the left, a traditional programmed robot will just crush it or miss it entirely. But in the last 5 years, especially leading into 2026, we have seen a massive shift toward more advanced robotics in the final assembly line. They use what are called SCARA robots, that stands for Selective Compliance Assembly Robot Arm.
I remember you mentioning those before. They are the ones that look a bit like a human arm but move mostly in a flat plane?
Right. They are incredibly rigid in the vertical axis but have some give or compliance horizontally. This makes them perfect for tasks like seating a central processing unit. They can move the chip over the socket with sub-millimeter precision, and because of that vertical rigidity, they can apply the exact downward force needed to lock it in without any tilt. They also use advanced computer vision systems, cameras that take a picture of the socket every single time to ensure no pins are bent before the robot even attempts to place the chip.
And what about the thermal paste? Daniel specifically mentioned that. It seems like such a messy, variable process.
For a long time, it was. But now, manufacturers use automated dispensing systems that are basically high-precision versions of an inkjet printer. They can dispense a specific pattern, maybe a 5-dot pattern or a complex honeycomb with a volume accuracy down to the microliter. This ensures that every single unit has the exact same thermal profile. No air bubbles, no overflow onto the motherboard. In some high-end laptops, they are even using robots to apply liquid metal thermal interface material, which is incredibly difficult for humans to do because it is conductive and can short out the board if a single drop goes astray.
Okay, but let's talk about the danger Daniel mentioned, static electricity. We are taught to wear those little wrist straps when we work on a computer, but how does a giant metal robot avoid frying a sensitive chip?
That is a huge part of the factory design. It is not just the robot, it is the entire environment. The floors are made of conductive materials that are grounded. The robots themselves are grounded through their frames. But the coolest part is the air.
The air? You are telling me they have high-tech air.
Yeah, they use ionizers. These devices blow air that has been electrically charged with both positive and negative ions. This neutralizes any static buildup on non-conductive surfaces, like the plastic casings of the components or the robot's own protective covers. It basically creates a static neutral bubble around the entire assembly line. They also use carbon fiber infused grippers on the robots that are naturally dissipative, meaning they bleed off any charge slowly rather than letting it spark.
That is fascinating. So the robot is not just a mechanical arm, it is part of a whole climate-controlled, electrically shielded ecosystem.
Exactly. And they have sensors that constantly monitor the electrostatic discharge levels in the room. If the humidity drops too low, which makes static more likely, the system automatically adjusts the HVAC or increases the ionizer output. It is a level of environmental control that you just cannot replicate in your living room, no matter how many anti-static mats you buy.
So, we have the SMT line for the motherboard, and these Scaro robots for the big components. But what about those tiny wires Daniel mentioned? The ones that connect the front panel buttons, or the tiny Wi-Fi antennas in a laptop. Surely a robot isn't doing that?
That is still the holy grail of automation. In many factories, even the most advanced ones, you will still see a line of human workers at the very end of the process. They are the ones plugging in the tiny ribbon cables and routing the antenna wires. Those tasks require a level of fine motor control and visual recognition that is still very expensive to automate. However, the industry is fighting back by changing the design of the computers themselves.
How so?
Have you seen the new cable-less motherboard designs? Companies like ASUS and MSI have started moving all the connectors to the back of the motherboard. This is not just for looks. It makes it much easier for a robot to plug things in because the connectors are in fixed, predictable locations on a rigid board rather than being at the end of a floppy cable. We are seeing a move toward board-to-board connectors that just snap together when the parts are pressed into place.
So they are designing the computer to be robot-friendly.
Exactly. But where cables are still necessary, we are seeing the rise of collaborative robots, or cobots. These are robots designed to work right next to humans. They have sensors so they do not hurt you if they bump into you. In some modern plants, you will see a cobot hold the laptop chassis at a perfect angle while a human worker uses both hands to snap in the delicate connectors. It is a partnership. The robot handles the heavy lifting and the perfect positioning, while the human handles the squishy part of manipulating the flexible cables.
I love that image. It is like a high-tech version of, hold this for me while I fix it.
It really is, and it solves the precision problem. The robot handles the finicky part of holding things steady to a fraction of a millimeter, while the human handles the complex part of manipulating the flexible cables. It is the best of both worlds.
You know, thinking about this makes me realize why repairability is such a hot topic. If these machines are designed to be put together by high-precision robots and specialized jigs, no wonder it is a nightmare for Daniel to fix them with a standard screwdriver.
You hit the nail on the head, Korn. This is the hidden cost of our miniaturized world. When an engineer at a company like Apple or Dell designs a laptop, they are not designing it to be easy for a human to open. They are designing it to be easy for an automated or semi-automated line to snap together. They use adhesives instead of screws because a robot can apply a precise bead of glue in 2 seconds, whereas a human has to fiddle with a screw for 10.
Right. They can use tiny, non-standard screws because they have a robot with a specialized bit and a torque sensor that will never strip the head. They can use adhesive instead of clips because they have a machine that applies the exact amount of heat and pressure to set the glue.
And that is why we see this push for right to repair legislation, which has really gained teeth in 2025 and 2026. It is basically asking manufacturers to consider the human element again, to use screws we can actually see, and to avoid gluing things down that will eventually need to be replaced, like batteries. The European Union has been a huge driver of this, forcing companies to make components like batteries user-replaceable again.
It is a fascinating tug-of-war between the efficiency of the machine and the autonomy of the owner. But speaking of efficiency, I want to go back to the free assembly thing for a second. We talked about how it is a loss leader for shops. But what about the environmental impact? Does this highly automated OEM process make computers more or less sustainable?
That is a double-edged sword. On one hand, automation is incredibly efficient. There is very little waste. A pick-and-place machine does not drop components on the floor or bend pins. That means fewer raw materials are wasted in the manufacturing process. The energy used per unit is also much lower in an automated factory than in a manual one.
But on the other hand,
that same precision makes the final product a black box. Because it was assembled with such tight tolerances and specialized tools, it is often impossible to upgrade or repair. When one tiny component on that robot assembled motherboard fails, most people just throw the whole board away. We have traded modularity for thinness and speed. We are getting better at recycling the raw materials, but we are losing the ability to simply fix things.
it is the classic trade-off. We want our laptops to be as thin as a notebook, but we also want to be able to swap out the memory. You can't really have both when you're pushing the limits of physics.
Exactly. And that brings us back to Daniel's experience. When he is peering into that box, he is seeing the intersection of these two worlds. He is seeing a device that was born in a world of microns and ions, and he is trying to interact with it using the tools of a world of inches and elbow grease. It is a fundamental mismatch of scale.
It really makes you appreciate the engineering that goes into these things. It is not just the software or the speed of the chip. It is the physical reality of making millions of these things work perfectly every time. The fact that a computer even turns on after being shipped halfway around the world is a miracle.
It is a miracle of logistics and physics. Every time you turn on a computer and it actually boots up, you are seeing the result of 1,000 different robots and humans working in perfect synchronization. From the SMT line in Shenzhen to the technician in Israel or the United States who did the final assembly, it is a global relay race of precision.
So, for the listeners out there who are thinking about building their own rig, or maybe just peering into the one they have, what are the big takeaways from this?
The first one is respect the torque. If you are working on your own hardware, do not over-tighten those screws. You do not have a $5,000 torque sensing screwdriver, so go easy. Tight enough to stay, but not so tight that you feel the board flex. If you see the PCB bending, you have gone way too far.
Good advice. What else?
Static is real, but you do not need a clean room. Just touch a grounded metal object, like the case of the power supply while it is plugged in but turned off, before you touch the sensitive bits. And try to work on a hard surface, not a carpet. You do not need an ionized air curtain, but you do need common sense. Also, avoid wearing that oversized fleece hoodie while you are handling a 4000 series graphics card.
And what about the finicky nature of it? Any tips for Daniel and his tiny screws?
Magnetic screwdrivers are your best friend. Some people worry about the magnets near the electronics, but for modern hardware, a small magnetic tip on a screwdriver is perfectly safe and will save you from losing those screws into the bottomless pit of the computer case. Also, use a headlamp. Shadows are your enemy when you are trying to find a tiny header on a black motherboard.
I have definitely spent more time fishing for drop screws with a flashlight than actually building the computer. It is a rite of passage.
We all have, Corn, we all have. Even the pros have a magnetic wand nearby for when things go sideways.
This has been such a deep dive into a world most of us never see. It is easy to think of computers as just these abstract things that run our lives, but they are very much physical objects, built with incredible precision and a surprising amount of human-robot collaboration.
And I think that is why Daniel's prompt is so great. It reminds us that there is a physical reality to the digital world. There are robots, there are humans, there are tiny drops of solder, and there is a lot of very clever engineering holding it all together. It is not just magic, it is manufacturing.
Absolutely. Well, I think we have covered the gamut here, from the economics of local shops to the ion-charged air of a global factory.
It is a fascinating journey, and it makes me want to go back and see if I can find that toaster I modified. I bet I could automate the buttering process with a Scara arm and a vision system to detect the crust.
Please, for the sake of the house and our insurance premiums, do not do that. I would like to eat my breakfast without a robot arm trying to achieve sub-millimeter precision on my sourdough.
No promises, Corn. No promises. I already have the servos in the mail.
Fair enough. Well, if you've been enjoying my weird prompts, we would really appreciate it if you could leave us a review on your favorite podcast app. It genuinely helps other curious people find the show.
It really does. And if you have a prompt of your own, maybe something about the physics of toast or the robotics of the future, send it our way. We love diving into the weeds.
You can find us at myweirdprompts.com, where we have our full archive and a contact form. You can also reach us at show@myweirdprompts.com. We are on Spotify, Apple Podcasts, and pretty much everywhere else you get your audio fix.
Thanks for joining us in the trenches of hardware assembly today. It has been a blast.
This has been My Weird Prompts. I am Corn.
And I am Herman Poppleberry.
Until next time, keep those screws tight and your static low. Goodbye.
Goodbye, everyone.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to another episode of My Weird Prompts, an AI-generated podcast featuring Daniel Rosehill's AI prompts, as answered by a revolving cast of friendly AI characters including me, Cornelius the Sloth. Subscribe on Spotify or visit myweirdprompts.com.